Hi, my name is Lucas. I'm interested in the following question. How do we know if two neural systems learn the same thing? These neural systems could be human brains, animal nervous systems, or artificial neural networks, like those used in two different robots. Let's consider the robot case. Well, we could start by sending the robots into the world and recording their neural activity. Once we have that data, we need a method for comparing each robot's activity to one another. Representation similarity metrics, or RSMs, are designed exactly for this purpose, to compare neural data between neural systems that may or may not have vastly different architectures. Using RSMs, we get an answer to a related question. Do neural systems compute the same representations? But is this the full picture? Does it answer the original question? Let's say that we get a confirmation that these two robots compute the exact same representations about the world. What would happen if we shock their brains or disrupt their representations in the exact same way? And button them back up and send them into the world? Can we have confirmation that the robots will fail in the exact same way? In other words, even if we know two neural systems compute the same representations, does that automatically mean that the two neural systems use their representations in the same way? Not necessarily. So, answering our original question, how do we know if two neural systems learn the same thing, requires answering two additional questions. First, do the two robots compute the same representations? And second, do neural systems use their representations in the same way? This second question has been previously neglected. RSMs have been designed to answer question 1, but can they also answer question 2? We designed some experiments to find out. We start by sending our robots into the world to collect their own representation. This looks like a representation matrix, which records the robot's internal features in response to a series of inputs. We call this matrix X. Next, we generate a new matrix, matrix A, by ablating or zapping some of the robot's internal features of the world. And now that we have our two representations, we can compare them in a variety of different ways. First, we can compute representation similarity scores between them to determine how much the representation changes as a result of the ablation. Then we can feed the representations back to the robot to determine how the robot fails. We call this a test of network performance. Finally, as a baseline, we assess how much linear information is lost as a result of the ablation using linear decoders. This is akin to just looking at the representations themselves without assessing how the robot's behavior changes. RSMs have been tested using linear decoders in the past. Finally, we generate our results. We do this by correlating RSM scores with either linear decoding or network performance changes. The correlations tell us how well RSMs satisfy criterion number 2 from earlier. We conduct these experiments on a variety of popular neural networks. We first find that RSMs do a good job of predicting linear properties of representations, as indicated by high correlation between RSM scores and linear decoding tasks. However, they do a significantly worse job at predicting how networks actually use their representations in the real world. So through the study, we have a hint of a problem. Even if RSMs do a good job of answering question 1, they are not guaranteed to be good at answering question 2. This study has exciting implications for improving interpretability tools used in neuroscience and deep learning. If you'd like to learn more regarding this finding and others, check out our paper in Transactions on Machine Learning Research in collaboration with Heejun Chun and Mikkel Carter. Thanks so much for your time.